All right, now in the previous section, the section on spanning sets, we showed that it's possible to find a set of vectors and consider their span and see that the span is in fact equal to the span of a smaller set. We did this example up here, example SCAD, where the span of W1, W2, W3, W4 was found to be equal to the span of just the first three. Okay, so the question is, how can we tell when we have unnecessary vectors in the set of vectors that we're taking the span of? How do we know that when we can throw out a vector and still retain the same span? So that's going to relate to this notion of linear independence. Okay, so let's go ahead and define the linear dependence for column vectors. Okay, so you can see linear independence. Linear independence is the opposite of linear dependence. Okay, now linear dependence and independence is a property of sets of vectors. It's not a property of individual vectors. It's a property of sets of vectors, and I should say finite sets. Okay, when you're talking about linear independence, you're probably going to be talking just about a finite set of vectors. Okay, so let's go through this definition of linear dependence for column vectors. Okay, so given a set of vectors S, a true statement of the following form, linear, this is just a linear combination of those vectors, right? They talk this vectors U1 through UN. If I can find a linear combination that gives me the zero vector, then this is called a relation of linear dependence on this set of vectors. In other words, if I can find a linear combination of a set of vectors such that the linear combination gives me the zero vector, then there's a relation of linear dependence on that set. Or I can say those vectors are linearly dependent. Okay. All right, so if this statement is formed in trivial fashion, if all of the coefficients are zero, this is called the trivial relation of linear dependence. Now, usually we don't even consider that. Usually when we talk about a relation of linear dependence, we're only talking about the case where at least one of these coefficients is not zero. Okay, so a set of vectors is linearly dependent if there's a relation of linear dependence that's not trivial. In other words, I can find non-zero coefficients that will make this statement true. Okay? In the case where the only relation of linear dependence is the trivial one, then S is linearly independent. So there are two options, linear dependence or linearly independent, because the trivial relation always holds. Okay, but in some cases, when the vectors are linearly dependent, then there are other relations besides the trivial relation. Okay, this should be reminiscent of what we talked about in homogeneous systems. We know that the trivial solution is always a solution for a homogeneous system, but some homogeneous systems have other solutions as well. Okay, so you can see that there's going to be a relationship between this and what we've seen before. Okay, let's look at some examples. Okay, so here's a set of vectors. All right, we've gone through this before to determine whether these can have a relation of linear dependence. We form this equation here. If this equation has a non-trivial solution, then we have a non-trivial relationship of linear dependence among these vectors. Okay, so let's go ahead and find this relation. We take this is a homogeneous system, so we can take the vector of the matrix of coefficients, find the row reduced form. Look, this does have non-trivial solutions because we have 0 rows here. We have one free variable, and we can go through the procedure. You can find a solution, and any multiple of this vector will be a solution for the constants. Now this looks like a vector, but these give me the constants. These give me the constants that I can put in for alpha 1, alpha 2, alpha 3, and alpha 4. If I put these constants in for alpha 1, alpha 2, alpha 3, alpha 4, and you can verify that you will in fact get the sum of these vectors with these constants gives me a 0. Okay, so that means that we have a non-trivial relation of linear dependence. So the set of these 4 vectors is linearly dependent. All right, let's consider linearly independent. Same thing. Have a set of vectors here. See if you can form a linear dependence relation. Then go and to do that, you find the matrix of coefficients. You row reduce. Look, there's no free variables at all. So the only way for there to be a solution, is if all variables are 0. Okay, so there's only the trivial solution. These are linearly independent. Okay, so as I mentioned, there's a relationship between linearly independent vectors and homogeneous systems. So let's look through this theorem. Suppose we have n vectors in vectors in Cm. What does that mean? That means that each one has m components. These are column vectors that have m components each one. Okay, so that means that if I take the matrix whose columns are these vectors, I'm going to have a m by n matrix, because each vector has m entries and I have n vectors. Okay, then this set of vectors is linearly independent if and only if the homogeneous system corresponding to this matrix has a unique solution. All right, just say that again. Take a set of vectors, form the matrix whose columns are these vectors. These vectors are linearly independent if and only if the homogeneous system corresponding to that matrix has only the trivial solution. Okay. All right, and that really is just the relation that we've talked before. If this system has only the unique solution, it must be the trivial solution. So that means the only relation of linear dependence is the trivial one. Okay. And you can go the other way as well. Suppose that this does not have a unique solution, so it must have another solution, and that must be non-trivial. If I have a non-trivial solution, then I have a non-trivial dependence relation among these vectors, so these vectors are not linearly independent. Okay. Okay. All right, so more examples. You can work through these and take a look at those. All right, now we noticed in the previous examples that we had linear dependence if we could find free variables in the solution, in the row-reduced matrix. And if there were no free variables, then there was only the trivial solution and the vectors were linearly independent. So we're going to formalize that observation in this theorem. Suppose I have a set of vectors, and A is the m by n matrix whose columns are these vectors. Let B be the matrix in reduced row echelon form that's row equivalent to A. Let R be the number of pivot columns. Then S is linearly independent if and only if n equals R. And that is, so what that means is that means no free variables. Okay. Okay. Now this is just applying stuff that we've seen before. That we know that if the number of pivot columns is equal to the number of columns, then there are no free variables. So the homogeneous solution system has no non-trivial solutions. Okay. So here's some more examples of this same thing. Okay. All right, so a special case of this, or something that follows very quickly from this, is that if there are more vectors than the size of the vectors, then S is a linearly dependent set. In other words, if I have a matrix that has more columns than rows, and I take these columns and consider them as vectors, so if I have n bigger than m, so that means more columns than rows, then these columns are definitely linearly dependent. Now, why is that? Because you can't have more pivot columns than you have rows. So you must have some free variables. If you have free variables, you have non-trivial solutions to the homogeneous equation, which means that the vectors are linearly dependent. So that all works out as we expect.